Section 4, Algebra Essentials. What do we have here? We have fractions, absolute values, exponents, okay, those kind of things. Let's begin with the fractions. Here are the rules, but can you read these? Let me expand the font. Okay, alright. Multiplication. Well, that's simple. We just multiply the numerator and denominator like this. That's it. Now, how about division? Remember that division is same as multiplying the reciprocal. So flip-flop the numerator and denominator, and then do the same thing. Multiply out the numerators and denominators as before. And there you go. Alright, how about the addition? Well, we have to cross-multiply the denominators and then add up. Well, it looks a little bit complicated, but this is no different from something we have been doing all the time. Say, for example, here's an example where we have the same denominator. In this case, what do you get? Add up the numerator, right? No problem there. Now, what if you have two different denominators like this? In that case, you cannot simply add up, especially the denominator. No, it doesn't work this way. How do I make it work? Remember this trick? Multiply the same strategic number to both numerator and denominator, and that strategic number is the other denominator. And this way we get the same denominator. And thus we can simply add up the numerator. We have been doing this from elementary school, and that's what we have over there. Written in a little more abstract fashion, but essentially the same thing. No difference. Now finally, how about the division? If you divide fraction with another fraction, then you get the denominators over denominators and denominators of the numerators. It's too complicated. So let's simplify by multiplying out all the denominators, all those, and then multiply that product to both numerator and denominator, to everything. So what did I change? I didn't change anything because BD over BD is 1, so multiplying by 1 does not change anything. Does it simplify though? Yes, it does. I can kill off this denominator and I can kill off that denominator, and then we get, well, in the end, something like this. And that's how you can do the division. And then simplify so that you get just one fraction, master fraction. Alright, so much for fractions, and let's go to the next topic there. Next subsection is about absolute values. Okay, what is an absolute value? I believe everybody can do this kind of computation easily. Oops. Just take the number part. But then again, what if the inside is a character? In that case, it can be a little bit tricky, so let's remember this. Inside was -7, but by taking extra negative, I can get it to positive, and we get the number part. So remember this part, which I'm highlighting in red, and then I can take care of that. Oh, no, excuse me. This entire inside, so this -7, and then I can take extra negative to make it positive, and that's what we have here. This A is, for example, -7, as we have down there, and then this extra negative makes it positive. Of course, if the inside is already positive, you don't really have to do anything. Just leave it there, and that's line 1. Line 2 is things like this. And this extra negative business is quite useful if you have characters or equations. If you have numbers, then it's easy, but if you don't, then you need extra negative. Alright, so much for absolute values, and how about exponents? Okay, everybody must be already familiar to all these. Repeated multiplication of n times, and then 0 power is 1, and then first power is itself, negative first power is reciprocal, and negative nth power is 1 over nth power, 1 over repeated multiplication. Among these, I see a lot of mistake from here. A to the 0 power is 1, not 0, it's 1. I see that mistake a lot. One good way to remember all those is to do this. Start from the multiplicative identity 1. That's where we start. And then multiply a one time. We get that. Just a. Twice we get a squared, a times a. Thrice we have a to the third power, a times a. 19 times, then we get 19th power, and so on and so forth. Now, what if I repeat multiplication 0 times, or not at all? Then we must stay at the starting point 1. And that's where this thing is coming into play. If I do not multiply anything at all, then we stay at 1, because the starting point is always 1. So a to the 0 power is 1. Now what if I go backward? Negative 1 is going backward. Well, we have to do backward of multiplication, so that's division, and that's where this thing is coming into play. Negative first power is reciprocal, and then repeat it, then you get negative nth power. See? Repeated division, or 1 over repeated multiplication. In the end, what we get? 0 power is 1, first power is itself, negative first power is reciprocal, and then negative power is denominator. Now what if you have a fractional power? In that case, we get a radical. So the denominator becomes that radical. And in this case, we're going to restrict the inside as positive. Yeah, I know there are people who are doing this, including our own textbook author, by the way. When we have odd radical, allow the negative number, and do something like this. There are people doing that, but not me. I'm not going to do it this way. I'll simply consider the positive numbers only. No negative number in any radical for simplicity. After all, this is 1324. We should keep simple. Also, there's a good reason, very good reason to exclude all negative numbers inside any radical. And it has something to do with complex numbers. In any case, let's keep it simple. Positive numbers only. In that case, we get radical. By the way, what do you mean by radical? Nth power is the inside. That's what this thing is all about. Okay, so much for exponents, and excuse me, not so much for exponents. We just did definitions. We have to do some more arithmetic. Let's see, we have some exponents and fractions, so a bit bigger font is in order so that we can read better. Now the first rule tells about the same base and different powers. Second line is about same power, different bases. Let's go back to the first line. A to the n power times a to the n power, just add up the power. Now if you have division, we go opposite. So we subtract. You see, multiplication, division, the opposite. Addition, subtraction, the opposite. And the third rule may be a bit hard to understand, but here we go. If you have power of power, then you have to multiply the powers. Here's some examples that'll help you understand. A to the second power times a to the third power. Second power, a times a. And third power, a times a times a. multiply all those together, total 5 times. Same idea will work to a to the 12th power times a to the 34th power. Just total how many a's multiplied. So we get this. Now, the opposite case, if you divide, then basically we are dividing these away. These will be crossed out, you see. And then what's left will be the third power in this case. If you have 7th power over a third power, then 4 a's will left. So we have 7 minus 3, we have 4th power, and so on and so forth. Now, if the denominator has more a's, then after canceling all those out, we have leftovers in denominator. So we get negative power, but that's the same as just straight ahead subtraction. Now finally, here's a visualization for this kind of thing. A squared is a times a. That repeat is 3 times. So total how many? Total how many bunches? 3 times. So basically it's a multiplication. See, if this had been 4 times, then we'll have one more of this. One more bunch is a multiplication. These kind of examples will help you understand why these are the cases. Now, what about the final rule here? Different bases, same powers. You can distribute the powers. Again, some examples will help you. AB to the third power, for example, write AB times AB times AB and then change the order of multiplication. Yes, you can do it. Multiplication is commutative. So we get a to the third power times b to the third power. You can repeat this argument for any nth power. I don't care whether it's 30 power or 300 power. Just multiply all the a's first and then b's later. Same idea applies for division as well. Instead of considering as division, consider as multiplying all the fractions and the numerators and denominators separately. So a to the nth power over b to the nth power. I didn't write the rigorous proof, but those examples will probably help you understand the general cases. And as for working out the general cases, yes, you should know how to utilize those. Not the proof, but how to use those, yes. Final comment. There's some common mistakes. Oh, again, we have some fractions, so bigger font is going to be better. This is a rare case that the separation works. You see, you can distribute the multiplication by the distributive law, and consequently, you can separate the numerator of a fraction. How does that work? The division, which I'm highlighting in blue, is same as multiplying the reciprocal. And then you can use a distributive property. In the end, you can separate the numerator like this. So, you can separate the numerator. But that is a rare case that the separation works. Otherwise, all know, look at this. A plus b squared is not equal to a squared plus b squared. You cannot separate it. 1 over a plus b is not equal to 1 over a plus 1 over b. You cannot separate denominator. Square root of a plus b is not equal to square root of a plus square root of b, and so on and so forth. Examples abound. All know. This is one of the rare cases you can, the numerator. Otherwise, all know. I don't see a lot of this mistake in college level, but the first and third I see a lot. By the way, as for these three, they work for multiplication for some strange reason, and I want you to think about those. Of course, there are examples that neither addition nor multiplications that can be separated. In any case, separating addition is a dangerous thing to do. So don't even think about it, unless you are in really special situation that you already know, the distributive property.